All right, next I'd like to look at the operation of a heat engine. And so this uses the principles of thermodynamics that we looked at in the last sections. And so the basic idea then with the heat engine is that we start out with heat at some higher temperature, TH, which leaves that reservoir and enters our heat engine. And then our heat engine, you can see in the middle there, this figure, is able to do useful work. And so this is the part of a heat engine that we like, the part that does the useful work. But then some heat is wasted, and so it's expelled at some lower temperature into a cold reservoir. And so there's some examples of this that I'd like to talk about. Here's our heat engine, and probably C, so it's consistent with what we have in that PowerPoint slide. So this heat that enters the system at higher temperature could be the gas that is being ignited in an internal combustion engine cylinder when the spark plug fires. Okay, so that could be where the heat comes in. And then the heat that is expelled from the system could be the heat that is either heating up the engine or is ejected by the tailpipe. And so that would be heat which then enters the lower temperature environment, which is basically room temperature, right? So you start out at some really high temperature, the temperature of the explosion, and then you go to some lower temperature, which is the temperature of the environment, and that's where the waste heat is expelled. But in the process of doing that, some of that energy, maybe 15% or so, of the energy from that explosion goes into turning the wheels of your car. Or you could have this heat that enters the system from a higher temperature be the radioactive decay of uranium into radioactive decay products like cesium and strontium and things that are also radioactive. But that in that process of the heat leaving that system, then it can do useful work. In this case, the system would be as the water expands in the nuclear pile, turns to steam, that steam then can turn a turbine. That turbine then can generate electrical energy in the form of electricity that we use in our houses. But then some of that energy is dumped out into the ocean. Okay? And so you might have a few billion gallons of water a day from Diablo Canyon that are ejected out into the ocean. And so if you went swimming out there near that ejected water, it would be like swimming around in a heated swimming pool, because you're right there in the ocean. So that is the wasted heat that can be used for further useful generation of electricity in that case. So they'd probably shoot you if you tried to swim in that water, and you might not want to anyway because you might be afraid of radioactivity, but that water should be pretty clean. And so if they allowed you to, it'd be like just swimming in a heated swimming pool. But that's not necessarily good for the marine creatures that are used to a lower temperature. And so that's perhaps a downside of the nuclear power plants that are located near oceans. But that, again, is an example of a heat engine, one that's completely different from the internal combustion engine. But in general, we can say that there are certain things that these systems have in common. We can say that QH, that's the heat that enters the system at higher temperature, has to equal W plus Q cold. Okay, so this is the wasted heat, and this is the useful work that is done. So this process then connects in the heat that leaves the system at a higher temperature to the amount of work that's done and to the wasted heat. Now here, I'm going to take these as being absolute values because it is a quantity of energy that's being transported. So here, energy is entering the system. Here, energy is leaving the system. But if we set it up this way, we aren't going to make any minus sign errors. So we sometimes call the efficiency of an engine like this E as equaling the magnitude of the work that's done divided by the total input heat. And turns out that efficiency can never be equal to 1 because some energy must be lost in the process of converting the heat into a certain percentage of it that is going to do useful work. There's just going to be a natural tendency for some of the elements of the system, the energy elements of the system, to be lost. And so we can rewrite this expression using the fact that W is equal to QH minus QL. It's the difference between the heat that enters the system at higher temperature and the heat that leaves the system at lower temperature. So that gives us here QH minus QL over QH, or that's equal to 1 minus QL over QH. And then associated with that, we have a percent efficiency that's equal to the E value times 100. And so that would be 1 minus QL over QH, absolute value, times 100. Okay, so let's say that in a given cycle, the heat that enters the system, let's say in 60 seconds, heat that enters the system is 1,000 joules, and the heat that leaves the system at a lower temperature is equal to 800 joules. Then from that, we should be able to find the work that's done in 60 seconds. W would be equal to the magnitude of QL, QH minus QL. And so that would be 200. And the efficiency then would be equal to W over QH, which would be 200 divided by 1,000 in that 60-second time interval. So that would be 0.2, or 20% efficient. And so that would be the way that we could use this information to compute the efficiency. And it turns out that efficiencies on the order of about 20% are actually fairly good efficiencies. That doesn't sound like it's very good, but in terms of the limitations that we have in a system like this, that turns out to be a good number. Now, if we're not given information in this form, we might wonder, well, how would we calculate the work that's done? Well, again, we could go to a pressure volume curve. Let's look at a very simple pressure volume curve. Now, in a heat engine, this must be a cyclic process. Because it's going to have to come back around to its original position again at the end. So you'd have some kind of a pressure volume curve. It might look like this. But then it would have to come back around and then repeat itself over and over again. So it's always a closed curve. Now, an arbitrary curve like this is hard to analyze, but we can look at a simple curve in which we have constant pressure and constant volume processes occurring all the way through. And this gives rise to an easy area under the curve. That's the reason why we're doing it this way. So you go from A to B, B to C, C to D like this. Then we can see that in these processes of going, say, from D to A and from B to C, there's no work done. But in the process of going from A to B and C to D, we have just the area under the curve. So from A to B, the work done is going to be this total area here. But then, in going from C to D, that's going to be negative work done. And so that's going to take away from it by that amount. So what we're going to be left with, because there's no work done during the B to C and D to A cycles, is that the total work done is the area enclosed by the pressure volume curve during one cycle. And so although it's easier to show for a process like this doesn't really represent any real physical heat engine. This is just a way of showing what the total work done should look like in general. But we can show that in fact is true in general for an arbitrary curve. So for any arbitrary heat engine cyclic process in which the pressure and the volume change a lot, but comes back to some same point at the end, the result that we got here in this simple geometric example, although I'm not proving this here, I'm just stating that the area enclosed by the pressure volume curve during one cycle is equal to the total amount of work that's done. And so we might wonder then, well, under what conditions could we have the maximum possible efficiency? And it turns out that that occurs during a what's called a Carnot cycle. That it's not 100%. You can't have a 100% efficient heat engine. And the Carnot cycle proves it. So this Carnot engine is not a practical engine. As a matter of fact, it's a super slow engine. It would take, for it to go through one complete cycle, it would take a couple of days. So it has no practical applications. But in terms of giving us an expression for the kind of a process that can produce the greatest efficiency, what this means is that if we can construct our pressure volume curve for our heat engine so that it has as much of the look of a Carnot cycle as we can, then that is going to give us the maximum possible efficiency that that system could have. So that's something always to shoot for. And so in a Carnot engine then, if we go from point A to point B, this is isothermal. So this is the part that takes a long time. So if we have an isothermal expansion, you have to maintain thermal equilibrium with the environment while the heat is being exchanged. And so for that to happen, the process has to go very slowly. Otherwise, you can't maintain thermal equilibrium. If you have a difference in temperature, that'll speed up the process of expansion. But while it's doing that, it's going to do so because of a difference in the temperature. And so this isothermal expansion is the first part of this. Then from B to C, we have an even steeper curve here, which is called an adiabatic expansion. So it's allowed then to expand quickly with no change in heat in the system. And then from C to D, we have an isothermal compression. This again will take a long time, because to maintain equilibrium, you can't, if you start to expand a gas, you expand it a little bit, but then you've got to let it achieve thermal equilibrium again with the environment, and then expand it again. It'll cool off, but you have to wait for it to absorb energy, so it's back up to so it's in an increment of little tiny stages where you've then, okay, now we've got to wait for the thermal equilibrium to reestablish itself. And so that's why it takes so long for these isothermal things to happen. So here, this is an isothermal compression. And then finally from D to A is an adiabatic compression. And so then the area under this curve, contained within this curve, swept out by this curve, is the work that's done. Here during the isothermal expansion, heat is absorbed from the external environment in order to keep this object expanding. When it compresses, heat is liberated from the environment. But if you work this out, and this is done in your textbook, you can show is that the efficiency, E Carnot, is equal to 1 minus QL over QH. That for Carnot, that's equal to 1 minus TL over TH. So in other words, Q over L, or QL over QH, I should say, is equal to TL over TH for a Carnot only. And this defines the lowest possible efficiency that a system can have between two different temperature reservoirs. So for example, we might want to find the Carnot efficiency if you have, say, a temperature TH here that's equal to 373 degrees centigrade and goes to TL, which is make this 127. Let's make this 27 degrees centigrade. Okay. So TH and TL will write like that in degrees centigrade. But remember that this is a temperature and not a change in temperature. So immediately has to be converted in degrees Kelvin. So this would be 300 Kelvin, and then here this would be 400 Kelvin. Okay, so the E Carnot for this would be equal to 1 minus 300 over 400, and that would be equal to 0.25, or a percent efficiency of 25%. 25% would be the maximum possible efficiency. So let's say that you find that your heat engine has a QL over QH that's equal to 200 over 1,000, like we had in that last example that I did. So that, I'm sorry, QL is 800 over 1,000, so that'd be 0.8. And so 1 minus 0.8 would equal 0.2, or 20%. That's what we got in that last example for our just regular old heat engine. So we have 20% efficiency, but what some people will do, for example at Diablo Canyon, I've heard of them doing this before, is they'll take their efficiency and instead of comparing it to 100%, they compare it to the maximum possible efficiency, because they say, well, hey, you know, you can't get any better than this, and so why are we comparing it to 100? It just makes our results look worse. You know? And so they go, instead of saying it's 20% efficient, they take the ratio of 20% to 25 and they get 80%. They go, so Diablo Canyon is 80% efficient. You know? And so that, although that's not true, it's a distortion of the truth, but it's not completely false either, because the best you can do for this particular example would be 25%. And so if you're at 20%, that's actually not too bad in comparison to the maximum possible efficiency. Okay. And so that's the way then that oftentimes we compare efficiencies of different thermodynamic processes to each other and also to the Carnot cycle. And so let's look at a more practical example. Look up at the data projector. And this is called the Otto cycle, which is the cycle for the internal combustion engine. So I'm just going to go over this conceptually, not actually going to punch out any numbers with this, but I think that it is a useful example to look at. And so in the Otto cycle, what we start out with is point A, and then that's at some lower temperature and larger volume. Then we have a compression to point B, and then we have a sudden increase in pressure, and that occurs when the piston is experiencing an explosion from the spark plug igniting the gases. And then this gives rise to a power stroke, and then at point D, you open up the exhaust valve and you let out the unburned exhaust vapors and let them go out your tailpipe. And so that'll be the heat which leaves the system at our lower temperature. Okay, so let's just look at this in a little more detail. So here's our pressure volume curve, and this is point A. So point A over here is going to be with our system at a maximum volume and 1 atmosphere's pressure. And let's say that we have the correct gas-air mix at point A. Now, I'm not going to explain to you at the moment how we got the right gas-air mix in here. But let's assume that we have the correct gas-air mix. But it hasn't been compressed yet. And the piston's getting ready to push up on it. Okay, and so this is at its maximum volume. So that corresponds to this volume here, Vmax. So that's this volume here, Vmax. And now, what we're going to do is we're going to close everything up, and we're going to compress it to point B, adiabatically. What does this mean? It just means we'll do it fast. Okay, so this thing's moving up and down pretty fast. These pistons are going up and down really fast. That doesn't mean that you don't need a radiator, though. A radiator helps to dissipate heat, and so that means that you actually are expelling heat. But it's not much in comparison to the total energy in one cycle. So that's why you still need a radiator, but we can still define these processes being adiabatic, approximately. Okay, so we go from point A to point B. So here's point B then, here. The piston is up higher by an amount equal to that compression ratio we talked about before. So this is V minimum here. Vmax. Okay, and so we've got a much more highly compressed gas-air mixture at point B. And the spark plug is not fired yet. Then we go from B to C, and we have a spark plug in here. And so that spark plug fires. So here then, we fired the spark, and then the gas expands to point C. Okay, so this is point C then, the piston drops, and the gas expands. The piston stays its place. The gas heats up. That's what I meant to say. So we get an explosion. Gas heats up, but no volume change. So in other words, it's heating up, so that's caused the pressure to rise. So that's what's happened here. The pressure has gone way up because the object is hotter, but it's at the same volume. So this is an it's called a constant volume or isochoric process. And while that's happening, this is where the heat enters the system at a higher temperature. Okay? And so it's come then from the change in the potential energy, basically, of the gas-air mix becoming oxidized, having a rapid oxidation process, which then gives rise to basically an explosion. It just, and it goes really fast, okay, because explosions happen quickly. All right, and so the piston hasn't moved then at all here. But maybe it's moved a little, but in the amount of time that it takes for the explosion to occur, we just have a much more highly energetic kinetic energy for the molecules that are in the system. And so now it's ready then to expand back down to point D. So from C to D, we have the power stroke. So that's the big payoff. So the gas then expands adiabatically. Which means quickly, to point D. So while that's happening, here's our gas, here's our piston now, and now our piston's back down at the original volume, which is V max. And the piston has been driven down, and so that's what gives rise to the useful work that's done. So this useful work is the area under the curve from C to D, that it's being dragged along during this part of the cycle because it has to be compressed. So that means other pistons have to be doing the work for this piston during this part of the adiabatic compression process. That's negative work that's being done. And then the work that's being done during the cycle is the area enclosed by this pressure volume curve. Okay? And so this expands then to V max, and this is when the useful work is done. This is the big payoff. Then we go from D back to A, and so here the exhaust valve opens. And at this higher pressure, the gas flows out through the tailpipe. At lower temperature. But if you feel the exhaust coming out from the tailpipe, it certainly is warmer than the external environment. And so you'd say that, well, that's wasted heat. That's like in Diablo Canyon where you've got that water that's shot out into the ocean that warms up the water. Here, this is creating heat pollution, but it's also creating particulate matter pollution as this unburned gas vapors and things are expelled into the environment. Okay, and so here the exhaust valve opens and this thing equilibrates to 1 atmosphere's pressure. And then, if this is a 4-stroke engine, then it does an extra cycle here, where it goes from A to A prime and then back again. Okay, so it goes up and down, but then it continues to be compressed, but with the exhaust valve open. So the exhaust valve stays open. And the gas volume goes to the minimum value. So this ensures that we've basically got all the exhaust out, or at least as much as we can get out, as it goes from A to A prime. And so this is happening at atmospheric pressure. So this is 1 atmosphere. And then, depending on our compression ratio, remember we did a problem before where we figured out what the pressure would be here based on an adiabatic process. We got like 3 atmospheres or something like that, 3.2, whatever. And then it really goes up when the expansion happens here. Okay. And so as we're going from A to A prime, then the exhaust valve stays open. The rest of the exhaust is pushed out. And then at A prime, the exhaust valve closes and the intake valve opens. right? So here we're up here at the minimum volume, and so then with the intake valve open, the piston drops, and that essentially sucks in the gas-air mix from the fuel injection. It used to be carburetor. Okay. And so that's what brings us back to point A, and so we draw in the correct gas-air mix. And then we start over at point A, and we begin the process again. And so then the process just continues. So we go from A to B, that's adiabatic compression. B to C, the gas-air mix is ignited by the spark plug and creates a constant volume increase in pressure as the heat is absorbed. We have the power stroke. Okay, and during the power stroke, then we get our useful work done. Then we release the heat at lower temperature, and then we get rid of all of the excess exhaust by letting it go through kind of a passive A to A prime, which is the exhaust valve open, and then the intake valve open, going from A prime back to A. So that connects it with the environment and maintains the pressure at 1 atmosphere during that process, in which either the exhaust valve is open or the intake valve is open on the way back in. And then it's ready to go again.